Hello again, this is Dr. Eid, Physics Made Simple. Today's topic is forces made simple. Today's agenda is going to be going over Newton's first law of motion and second law of motion. We're going to have multiple examples using net force, balanced and unbalanced forces. We are also going to add friction and tension, and we're going to use a couple of examples, sliding with friction and hanging mass and tug of war. So let's get started. Looking at this book over here, there's a book sitting on a table. Let's go ahead and try to list all the forces acting on this book, and let's try to draw a free body diagram. The first thing I want you to remember is that when we are drawing a free body diagram, we are identifying all forces acting on the object. The force going upward is going to be called the normal force. The force going downward is going to be the force of gravity. If there's a push or a pull, then we will identify it in the left or right, depending on which direction the extra force that we are having is acting on. So let's go ahead and take a look at what it would be looking like with just the book sitting on a table and drawing a free body diagram. As we can see, we managed to add two forces, one going upward, which is called the normal force, and one going downward, which is called the gravitational force. So, how do we make calculations in case we need calculations? We will identify the mass of the object, which is the mass times the gravity or times that force downward is going to be called weight. The normal force is upward from the table. Since this book is sitting on a table and it's not moving right or left, up or down, then we call it the book is at rest. There is an upward force that is equal to the downward force, and the net force, since it's not moving, is going to be equal to zero. The second example here, as you guys can see, is the first Newton's first law of motion. Um, this is what the inertia in action. And if you are to be remembering on a daily basis, what would be a perfect example for this would be sitting in your car and driving in your car and stepping on the brakes. You are in motion and the car is in motion. As you step on the brakes, you are forcing that car in the opposite direction. Your body is sitting in that car and it's going to continue to go in the direction of the car. It is not going to stop. And the only thing that's going to stop its back is your seatbelt. So your seatbelt will be holding you back by using a force in the opposite direction. But the normal, what we see is the inertia in action as you move forward within the direction of the car. So if we look over here, we can see also a perfect example is if your bike ends up bumping on something, making a quick stop or a quick force to make that stop. Your body is naturally is going to be going still in the direction of the bike, so that is called uh, object in motion is going to continue in motion, and object at rest is going to stay at rest, just like the book. So the book is sitting on the table, it's at rest, it's not going anywhere. You are in motion, you come to a sudden stop, your body is going to continue to go in that direction, and that is what we call inertia. This is another example of Newton's second law, as we have seen in my previous videos. So in this example, we're going to see the net force, or calculate the net force acting on an object, but there is no friction. So we see that we have a box, and that box has a force forward of 20 newtons. So the question says, find the acceleration of a 5 kilogram box being pushed to the right with a 20 newtons force and no other force is acting on it. This means that we have no force of friction due to the place the box is sitting on. So the net force with no friction is going to be using the Newton's second law uh, um, formula, which is force is equal to mass times acceleration. Moving those around, to calculate the acceleration, we are going to divide the total force by the mass. What is the total force? We have total force of 20 forward. And what is the mass of the object? It is 5 kilograms. So force over mass, or 20 over 5, is equal to 4 meters per second square. What does that mean? This means that this box is actually moving to the right at an acceleration of 4 meters per second. So this is another example, and we're going to see um, a force that is going in two different directions. Let's go ahead and read the question. It says a 15 newtons force pushes right on a 3 kilogram box, while friction is pushing left with a 15 newtons force. So if I was to push on this box to the right with a 15 newtons force, and the force of friction of the surface that the box is sitting on is pushing back with the equal amount of force, what happens? We are going to look to see what the acceleration of the box is going to be and what can we say about the net force. So the net force, obviously, I have force forward that is equal to the force backward. So is this box going to move? No, because as much as I'm pushing, I have something pushing back on me. So the acceleration of this box is going to be equal to 0 meters per second square. So this shows a balanced force and a velocity that is constant, and it could be 0. So this could be moving at a constant speed, which means it's not accelerating, it's not speeding up, or moving and not moving at all, and it could be 0. It's not even moving. That being said, let's go ahead and take a look at an unbalanced force. So in the case of an unbalanced force, we have a 10 kilogram suitcase uh, that is pushed on a floor with a 40 Newton force. So I am pushing a suitcase that has a mass of 10 kilograms with a 40 Newtons force. Friction from the floor is 10 Newtons. So we are supposed to find the net force and the acceleration of this suitcase. Let's go ahead and draw the free body diagram. We have a suitcase, 10 kilogram. The force forward is 40 newtons to the right. Force backwards, which is the force of friction, 10 newtons to the back. To find the net force, we subtract 40 newtons minus 10 newtons, and that is going to be 30 newtons to the right, okay? So that being said, can I find the acceleration? How fast is this suitcase going or accelerating? So moving the formula for the Newton's second law of motion around, the acceleration is the total force divided by the mass. Total force, or the net force, in this case is 30 newtons. Divide that by the mass of the object, which is 10 kilograms. It is going to be 3 meters per second square in the direction of the higher force, or to the right. In a case of a hanging mass, this is one of the first things that could come to mind when we talk about hanging mass, is basically maybe a gymnast or an elevator. Every day, you know, a lot of us use an elevator to go up and down. So let's go ahead and take a look at what happens to the tension in the rope, or uh, that that that's pulling us up if we were like a gymnast, or if the actual rope is pulling up an elevator. So in this example, there's a 40 kilogram soldier that is hanging from a rope, and uh, we know that there's going to be tension in this rope that is pulling upward, and the mass of that soldier being pulled downward. So if the rope is being pulled upward at 2 meters per second square, what is the new tension? Okay, so at rest, what's happening? The tension in the rope, or the force upward, is equal to the mass times acceleration downward. So the mass of the soldier is 40 kilograms. The acceleration downward is gravitational acceleration, so 9.8, so 40 times 9.8, that's 392 newtons. So that's at rest. He has not moved. Now, if we were to pull that soldier upward, or if that tension now changes to have an acceleration upward at 2 meters per second, what can we say about the tension? Okay. We know that the tension minus the mass times gravity downward, okay, should equal to, okay, so that's the net force, should equal to the mass times the acceleration upward. Okay, moving this around, we need to remember that g as well as this new acceleration, they're both accelerations, g downward and acceleration upward. Okay, so gravity, which is 9.8, acceleration upward is 2. Adding these two, multiplying those by the mass, because that's the mass of the person, that is going to be equal to 472. So the tension now changes from 392 to 472 newtons. Why? Common sense says, okay, I have a tension in the rope that is trying to pull this mass as well as this pull downward of the acceleration of gravity. Now, I'm not only doing that, there's also in the opposite direction, or in the direction of that tension, another acceleration. So we're going to add that acceleration to the already acceleration that we have of 9.8, and that's why we end up multiplying it by the mass of the soldier. Let's go ahead and have one more example. This is our last example for this video. It is an example of a tug of war. We have a cart that's full of toys, and we have two people that are pulling in the opposite direction on this cart. So the free body diagram of this object will be two forces, one to the right and one to the left. This picture that you have in front of you is from the PhET simulation example that I've provided in the previous video, so feel free to go to PhET simulations and play around with the forces, and hopefully get used to manipulating the forces and watching what happens. So in this example, we have two students pulling on a 12 kilogram cart in the opposite directions. One of them is 15 newtons force to the right, and the other one is 30 newtons force to the left. We need to find the net force and the acceleration of the cart. So net force is going to be equal to subtracting both forces, 50 to the right minus 30 to the left, and that is going to be equal to 20 newtons. In which direction? In the direction of the higher force, which is the 50 newtons, which is to the right. Now to find the acceleration, manipulating the F is equal to ma around, we go ahead and use A is equal to the net force divided by the mass, which is 20 newtons, which is the total that we just found, the total force or the net force, divided by the mass, which is 12 kilograms, and we will end up with 1.67 meters per second square. That is the acceleration of the cart. In which direction? In the direction of the higher force, or to the right. This is the end of this video. Thank you very much for continuing to watch my videos. Please drop any comments or questions, or feel free to email me and subscribe. Thank you very much, and have a nice day.